Hello, it's Keith here, and this is lesson 1 of my IBM370 Assembly programming tutorials. Now, we've gone through a wide variety of systems in my tutorials. We started with the Z80, we moved to the 68,000. We've gone back to the PDP-11, but I think this is going to be the earliest system that I've ever covered. We're going to be looking at what I'm referring to as the IBM370, but actually the instruction set we're covering, I believe, is entirely included in the IBM360. Now, the IBM370 was released in the very early 70s, about 1970 itself. The 360, I believe, came about around 1965. So these systems are far older than I am, and far older than all of the other systems I've covered. And it's really quite impressive how powerful this system is. But that said, there are some quite significant changes to the way we actually have to program it. So we're going to have a bit of an adventure here. So I'm going to be using the Hercules emulator or simulator, whatever you want to refer to it. I've got a pre-configured version that you can download from my website with the operating system hopefully set up in a way that you can reasonably easily use. Although actually I basically followed their online tutorial and got it set up anyway. Now, before we go into the details of the hardware any further, I want to actually start showing you some examples. So let's go over to the screen and let's see these running. Now, this system runs in quite a complicated way. There's basically 3 parts to it. There is the server itself, which will be running. There is a console, which is a terminal emulator, which will connect to that server for operating the server. And then there is the printer output, which we will be viewing in this window over here. Now, if all goes well, we can use my scripts to get this server started. So if we press F6 here, we've got a drop down here, and the first one we want to do is this Hercules job here. Now this is for an entire JCL file which we've got here. Now this is a job file. You can see my server here is starting up. I can't actually touch it because some send key scripts are going to be fired over to this. It's actually started up in an annoying position all the way over here. I don't know why it's done that. Move it over here. So that server is starting up there. Oh, that's actually the terminal emulator. I've got it mixed up. The server is here. We've got all of these windows, but we don't actually need to use these. So this is the server. This is the terminal emulator here. And then we've got our output over here. Our server's now started up here. If I now just run this again, this will now send it to the running server, and hopefully we will see the response pretty quickly. Okay, so here we've got I like pie. I am a really long line, so I need 2 lines because I'm so long or something like that. And these are actually lines in our text. Now what I'm going to do first is I'm going to change this line from I like pie to I like cake. And the reason I'm doing this is to check the server's really running and showing the latest text and not showing out-of-date text. So you can see here now it says I like cake. That's a change I just made. The server is running fine. And so this output here is a summary of the printer output. This would physically come out on a printer on the old server. If you go over to this screen here, this server isn't some little box that sits on your desk. It's not a Raspberry Pi. It's an entire room full of crap, basically. It's a crazy huge thing, and the actual server itself was a rack mount unit, but that didn't have disks, it didn't have a screen, it didn't have anything, and that's why we have to have all of these. That's our terminal that would control it. That is basically our emulator. The real hardware didn't have that. And then, as I say, this is actually our printer output. Now, when we wanted to create a job for this server hardware, we would, I believe, have to actually make it in punched cards. Now, one of my relatives actually programmed one of these back in the day, and what they told me was that they would provide the source code that they wanted to the people who would then basically create the punch cards and put it into the machine, and then they would get the output. And so it was literally a job that you would send away and you would get your results back the next day, kind of thing, or something of that effect. It's not like we get now, where we wait a few seconds and our announcement for our delight in cake comes back straight to us. It would be a far slower thing. And so the way you had to do your jobs, as I say, via punched card. And so what we would have to do is create a JCL. This is a job control language, and basically these lines starting in these slashes here, these are announcing the start of the job here and defining the various settings that we need to assemble this file. Now we won't ever need to change these in these tutorials. This isn't a JCL tutorial, this is an assembly tutorial. So we're just going to be looking at the ASM code. Now let's just quickly look at the contents of this file, and we'll start to understand some of the assembly syntax as we go along. So this is JCL, the slashes here, this is JCL, we won't look at that. So if our line starts in a star symbol, an asterisk symbol, that means this is a comment. Now I've put a semicolon in here, but that's just so that Notepad++ colors this in the way I like. The semicolon doesn't define a comment on this system. The star at the start of a line defines the comment, or the fact that it basically comes significantly after other commands defines that it's a comment. So this is a comment, even though it doesn't look like one, because they say it's in the correct position to be a comment. This is a comment because it's in the correct position to be a comment. It's not the semicolon doing that. But if we want a comment at the start of the line, we have to have an asterisk. Now, after this comment here, we've then got a bunch of equivalence symbols. So we're defining R1, R0, and all of these to be numbers. Now, these are going to be our register labels. We don't actually need to use labels for our registers. We're referring to some registers here, but it gets very confusing. So I like to use register labels wherever possible because it makes it nice and clear what's going on. But we're actually defining those as symbols, macros, if you will. And so that will be done in all of my tutorials. We've got a label here, hello. Now this is at the far left of the JCL file, and so that the fact that it's at the far left defines it as being a label. And you also have to watch your case on this system and your length, so don't be making any very long labels. So try and keep them under 8 characters or you'll have trouble. So we're defining the start of our section here and the end of our section down here. We've got a return command returning to the operating system. That's actually a macro. We'll see that in a later tutorial. We've got these commands here. Now these are defining that register 12 is being used for a special purpose. We will describe what that purpose is later on. It's too complicated at this stage. What we really want to look at the moment is the WTO macro. This stands for write to operator, and this is the equivalent of our print string command, if you will. This actually executes a whole sequence of other commands, which we will also look at later in another lesson. But basically at this point, we're just showing the message, I like cake, to the screen. We then want to show an even longer message, and so we've got this ridiculously long one. And again, this is all about the special positioning of certain characters, in the same way as this is a comment because of its position, and this asterisk defines a comment because of its position, and this label is a label because of its position, and this is code because it's tab indented and it's not at the same position as that label. This minus at the end here isn't actually a minus. It's actually defining that we want, this is the line continuation position, and this defines that the stuff on the next line is actually more of the same. And you can see we've had to indent that into the correct position for our code. Everything has to be tab indented to the correct positions. So it's a little bit frustrating. And if we go to our documentation here, you can see here we've got an example here, and this is defining the character positions and the correct positions. So our code commands should start at character 10, our labels can start at character 0, and our line continuation should be at character 72. So you can see these column positions are all very strictly defined, and if you deviate from this, you're quite possibly going to get assembly errors. So please bear that in mind. Now, a couple of important things to bear in mind. As I say, labels should be 8 characters, and basically I think pretty much everything should be uppercase. Commands and labels and everything I think are going to work best if they're uppercase. Speaking of case and characters, another thing that we do need to discuss, because it'll drive you nuts later on, is that the IBM370 doesn't use ASCII, it uses EBDIC, which you've probably never heard of if you are younger. And if you're my age, you've probably heard of it in a kind of a grumbling kind of way of, oh my God, not that thing. It's all to do with the punch cards. Again, EBDIC was designed around the ability to punch the cards, and it worked more conveniently for those, I believe. But we just have to use it. That's what this system uses. So get over it, basically, to be blunt. Another thing we have to get over, not so much though on this system, is the IBM bit numbering, as I refer to it. I actually should change that. It says PowerPC. that's because it's also used by the PowerPC. But the IBM bit numbering is the opposite of what everyone else uses. If you're familiar with the Z80, the 8086, the 68000, the least significant bit was always bit 0, and then they went up in ascending order. So the most significant bit would have the highest number. IBM370 and the PowerPC do the complete opposite, and the most significant bit is bit 0 and the least significant is bit 31. Part of that is the reason that the IBM370 has entirely 32-bit registers, which is absolutely staggering when you think of the age of this system. This system was 32-bit before the Z80 was 8-bit. Absolutely incredible. So that's another thing you need to bear in mind. And another thing you also need to bear in mind is some of these registers have special intended purposes. Basically, R13 is treated sort of like a stack. It's not called a stack, it's called a save area, but it's effectively like a stack. R14 is the return address. So this is the return address when our subroutines are called in most cases. R15 is the often used for the address that we want to call. R0 is often a hardwired 0. A lot of commands use that as a hardwired 0 with addressing modes. So probably best to avoid that. But basically R0 we want to avoid using for addressing modes. R1 and R2 we can really use in most cases for our own purposes. But R13, 14 and 15 on the IBM370 we shouldn't use. They have special purposes, and until we know what they are we should leave them alone. And believe me, it took me a hell of a long time to figure that out, because IBM do not like mentioning that in their documentation. All of the CPU documentation doesn't mention that because it considers it all to be OS documentation. I don't know why that is. Very frustrating. Anyway, that's it. Another thing, in my tutorials have some shared modules that we use for things like memdumps and for showing registers and things. So they also use R11 and R12. So please avoid using those. Try and restrict yourself with the registers R1 to R10. I think will mostly be safest for you when you're experimenting. Of course, if you're not using my code, you can use whatever the heck you want. It's just so that my tutorials have some helper functions to show registers and show memdumps and things. I use those. Now, the other thing I'm going to quickly mention is the condition code bits. Some systems have an entire register. The IBM370 has just 2 bits, and so this has a value of 0 to 3. And what that means depends on the kind of command we just ran. There's a lot of macros or pseudo commands that will actually make that easier for us to work with. So it's not necessarily something we need to massively worry about at this stage, but I just wanted to mention it because in this early tutorial I want to mention the registers that are available, the kind they are, and things like that. Okay, so we ran that JCL file before by pressing F6 and selecting Hercules job from my menu. Now that is I would suggest you run that to get the Surface started and just check it's actually started up correctly. Occasionally it gets clogged up, and maybe the printer file is over full and things. Another thing just to quickly mention is these scanning messages here. This is a little .NET app that I've written to try and find errors and the tail of the log files. The actual printer files may be huge, and this is just the last part of them. So this is summarizing them for your benefit. This isn't actually what the server is actually outputting. Now, if we've got an example from my tutorials, we're actually using a template header and footer, if you will, to our actual source file. So this ASM file is not a complete job, and it's not even a complete ASM file. So if we press F6 again, and instead of selecting Hercules job, we select Hercules job basic head foot. Now this will include my header and footer, which includes some helper applications like a monitor to dump the registers to the screen, a CC test routine, a memdump routine, and some print charm print string routines. You can see they aren't included here. They are included in the downloads. They're the header and footer that I'm including with that extra option. And so let's run this example here, and you'll see the output from this. Okay, so here we got all kinds of nice good stuff that's going to help us out in our learning about this system. So we are loading a sample register here, and we're running show hex 8, and you can see that is there. That 1, 2, 3, 4, 5, 6, 7, 9 is there. The exclamation mark was from that print char. Remember 32-bit registers, so we've loaded 4 bytes there into that register before showing it. We are loading 1, 2, 3, 4 there. The print line is actually dumping the line to the screen. It's all being loaded into a buffer, and so that would dump that entire line to the screen. we are using the monitor function. This is one of our best ones, and that is showing all of the registers to the screen there. You can see them all. So if you want to play around with registers and see what they do, you can do it with that as an easy way of showing all the registers to the screen. We have CC test as well. That will show the condition code value. So the CC contains the value 2. We can load in the address of some code here. Now, what we've got here is that we're actually effectively running this print sequence routine. That's just another thing. We're not going to cover that here. The more important one, though, is the memdump routine. So we are loading the address of hello here, and then we are showing 4 lines to the screen. And you can see here we've got all kinds of bytes here, and hello world there. We're showing that as EBDIC. Remember, not ASCII. Those are EBDIC bytes. So that's again, just another little tool to help you out. So this, if you're looking to go it alone, if you just want to completely ignore my tutorials, what I'd suggest you consider doing is you maybe download the dev tools and these are sample files, and maybe you modify this and you use that monitor and that memdump and maybe a few of the other bits to help you get started. Now, obviously, I've not just discussed what all of those commands do. We're going to go through them all one at a time. It's going to take a lot of time to really get into all of this and explain it all properly. So here was me just showing you this minimal experimental file that you can play with if you're really going it alone into the wilderness. If you're going to follow my tutorials, we're going to go through everything that basically this uses a little bit at a time in these lesson examples. So that's what we're going to do right now. Okay. So let's begin. So at the start of this file, we've got some reminders. So our script will append a header at the start here, and our script will append a footer at the end, right down here. It's quite a long file. So that's just to remind you that you're not seeing the entire file that is actually assembled by the server. So R0 generally available for you, but in addressing it sometimes does strange things, so I'd suggest you leave it alone until you get the hang of it. R1 to R10 are available for your use in my tutorials. I do use R11 and 12. Okay, so here is the actual start of our program. So what have we got here? Well, we've got this command here, and this save command is a macro, and we're backing up all of the registers for the operating system so that we can correctly return to the operating system later. So at this stage, I mean, you should really think of these as just being a template way to start your program. Now, the way a lot of these commands work that we will see later on, the assembler is actually converting them for us and doing things behind the scenes, and it wants a single register for its use to do those behind the scenes things for us. And so we need to tell it what register to use, and that's what using star comma does. We're saying use R12 for your purposes in calculating the addresses, basically. And that's what that is doing there. So this is telling the assembler to use R12 for calculating addressing, but then we need to load R12 with the correct address to calculate addressing. BALR is loading R12 with the current address. Now this should be a jump to subroutine command, but that 0 byte afterwards, that 0 there, specifies that it doesn't actually jump anywhere. But as I say, that's a little bit confusing, I know, I apologize. Just think of this as your template start of your program, and then at the end of your program you want this. So you've got you're loading R13 with OS return, and then you're returning here. These are a very strict template, if you will, for ending your program. Okay. Now at the start of our code here we've got some B's. This is branch, and these are going to jump to a branch to a label within our program. Now these are the different examples we're going to see in today's lesson, and you can see that 2 of them are commented out with an asterisk at the start. Remember, it's the asterisk at the start that comments out the line and not the semicolon. Now first of all, we're going to run example loads 1. Now we are also loading R11 with the address WTO text. This is for my tutorials. The routines we're going to use require this to be the case. Remember, I said before, R11 is used by my tutorials for the WTO buffer, and so this is basically whenever we're sending characters to the screen, they're actually being built up in a buffer using R11 and then being dumped later. So for my code to work, that needs to be set, and you need to leave R11 alone. Let's say if you're doing things on your own, you can use R11 for anything you want. Okay. So that's where we are. So let's take a look at our first command properly then. So the L command. L stands for load. So what we're doing here is we're loading a register with a value from an address. Now the register is on the left of the comma, and then there's the comma, and then the source is on the right. And you can see here we've got D2 and then open brackets x2 comma b2 close brackets. We'll worry about what that is in just a moment, but the first thing I want to point out is your destination is on the left of the comma, the source is on the right, and that's true for most of the commands on this system. Okay, so what are we going to do? Well, we're going to do some loads of literal values that are just straight away, here they are, these values here. So we've got the register destination, we're loading R0. As I say, in some cases it's a hardwired 0, but not in this case. We can use it just fine in this one. So we're loading R0 with a value here, and that is a hexadecimal value 1, 2, 3, 4, 5, 6, 7, 8. And then we are loading R1 with a value, and that is the value 1, 2, 3, 4, 5, 6, 7, 8. But F stands for full word. So this is actually a decimal number, not a hexadecimal number. If you don't know what hexadecimal is, I'll describe it briefly. It's base 16, essentially. We'll have a look at it on the calculator in just a moment. But if you don't know hexadecimal, please check it out yourself. I do have a tutorial on my YouTube channel. But if you don't know hexadecimal, it's a bit strange to be trying to learn a mainframe assembly language from the 70s. So you do need to learn that yourself. It's not something I'm covering in these. Anyway, and then we can also load a character sequence, of course, in EBDIC, remember, so we can do equals C, and then we can specify a sequence of characters A, B, C, D. Now the equals is specifying that we want to use a literal, and then the letter is defining the kind of literal we're defining. So all of these are loading these registers with various values. Okay, well, let's fire this example up and let's see if we get some results that we like the look of. Okay, so we can see we've got no errors. That's a good start. And then you can see we loaded all of these values. We also loaded R3 with a binary. I missed that one, I apologize. So B is binary, and then here's all of our binary bits, lots of them there. And then we are running branch and link to this address here, monitor 4, which will show 4. This is one of my subroutines. It will show 4 registers to the screen. R14 is specifying the address to use for the return address. We'll worry about branch and link a bit later on. And then we're running print line, and in this case we're actually just creating a blank line to make those results nice and clear. So let's see what the result of these loads was. Well, R0 was loaded with 1, 2, 3, 4, 5, 6, 7, 8, exactly as we specified in hexadecimal, the X hexadecimal there. R1 is loaded with BC 614E. Well, we tried to load it with 1, 2, 3, 4, 5, 6, 7, 8, but if we load up our calculator here, and if we type into our calculator 1, 2, 3, 4, 5, 6, 7, 8, we will see that value there looks awfully suspiciously like that value there. So we're showing, for convenience, we're showing to the screen in hexadecimal, but that is the same value that we specified in decimal. That's been loaded correctly. Now our ABCD with that C loaded into R2 has become C1, C2, C3 and C4. If we check our EBDIC table, if we check it here, we can see A, B, C, D are on the C line in columns 1, 2, 3 and 4. So those are also correct. EBDIC is rather a pain, but we have to deal with it. And we've also loaded our binary value here, and you can see that has been loaded in there. That is AF in binary. All of those bits are AF in binary. So that is what happens when we specify an equals. We are specifying a literal value. Now, when we specify a literal value, actually the IBM370 assembly language and processor can't actually store that in the same line of the resulting bytecode. It has to store an address and store the value somewhere else in our program. Every load command has to be specified as an address and an offset, and so it's calculating an address and an offset, and it's putting these values we wanted to store somewhere else. Well, where is it storing them? Well, quite simply, it's storing them at the place we specify as the LT_org. This position here, this LT_org command is telling the assembler, put all of your literal values at this address, there's no functional code going to execute this, so just put them all there. You can see we've got some other values we're specifying and we're defining as constants here. We've also got this CNUP command. Now this is a little bit tricky, but basically this is just checking we're 32-bit aligned before and after this literal section. If we weren't, our code would fail. So we need to be 32-bit aligned. We will always be 32-bit aligned with our regular commands. They are all 32 bits, whatever is in them. As I say, even these literals, it doesn't matter how long the literal is because it's not actually stored here, it's stored at that LT.org. So that's how that works. Now we will discuss the addressing mode in more detail, the actual addressing mode that is executed a little bit later on. So don't worry about that for now. Okay, so here we were loading these literal immediate values. What we're going to do now is we're going to load from an address, and so we're loading here R0 with the value at address hex value 1. You can see here it's FFEEDDCC. Now if we look at our second example here, you can see that has been shown to the screen here. Now what we're doing next is we're using another kind of load command, LA. Now LA stands for load address. So here we're loading R1, but we're not loading R1 from address hex value 2. We're loading R1 with the address hex value 2. And you can see R1 is actually being loaded with 95AFO here. Now what we're going to do next is we're going to actually load from the address in the register R1. And this is a little bit more like what the assembler is actually doing for us behind the scenes when we load those literals. So what we're going to do here is we're going to say load R2 with the value at the address in R1 plus an immediate offset of 0. So just the result is we're loading from the address in R1 here. And so R1 contained the address hex value 2. Hex value 2, you can see here, contains AA, A2, A3, A4 here. And so R2 loaded from that 0 offset will contain AA, A2, A3, A4 here. Now what we're then going to do is we're going to load R3 from the address in R1 plus an immediate offset of 2. Well, R1 contains the address hex value 2, and so that will be pointing to here, but then we're offsetting by 2, so we will be loading from 2 bytes along here. So we will end up loading, when we load our 4 bytes, A3, A4, BB, B2 because of this load offset here. And if we see R3, you can see that is exactly the value we've got. And so we are able to specify a source register which contains the address we want to load from and an immediate offset here. And that's basically what we were doing up here when we were specifying R12 to the assembler. So when we specify these literals here, what is being done by the assembler is the offset from our base here to our LT.org is being calculated, and this is actually being put in a command, basically in this kind of format here, in the actual resulting code of what we specified here. A little bit complicated, I know, but as I say, that is actually what's going on behind the scenes. Now there are some limitations to our valid offsets. Now if we just try uncommenting this line here and we try and run this again, we will actually get an error. What we're trying to do here is we're trying to use a negative offset from R1 here, but you can see here we've actually got an error here, and the error it's saying is the displacement is greater than FFF here. That displacement is negative and we can't actually do a negative displacement. Now I actually just noticed a bug in my bug code, a bit logical, but basically I had this written as 255 was the limit, but that's not actually correct. It's 4096 is the limit on this system. So our displacement can't be 4096 bytes away, otherwise we will also get the same error. But if we change this and we change this to 4095, and we run again, well, now that is actually valid. So our displacements can actually be pretty far away on this system. As I say, this is a very powerful system for its age, and because it is a fully 32-bit system, it has an awful lot of capabilities. So there we go. So there we've loaded in some values from literal immediates and from memory. Now what we're going to do next is we're going to try some other kinds of loads. Of course, we don't just want to load from memory all the time. We will actually want to transfer between registers. And for this we have the command LR, L for load and R for register, and this specifies the source is a register. Now load commands, the destination is always a register, and so this is specifying the source is also a register and not some kind of memory address. And this is something that's very common and very true for the IBM370. When a command ends with an R, then the source parameter is a register. When it doesn't, it's probably an address. So that's something we'll see along. So here what we're doing, the destination on the left of the comma, the source on the right of the comma as before. So we're loading R0 with the value in our register R1. And here we're loading R2 with the value in register R3 here. And we're dumping those results to the screen. And so again, if we look at our results here, well, here were our original values. And you can see here R0 has been loaded with the value that was in register R1, and R1 has been unchanged. And here you can see that the value in R2 has been loaded from R3, and R3 is unchanged. So there we go. So those are some simple loads. Some tricky stuff in there. I sort of apologize, but as I say, this is a mainframe system. If you're new to assembly and you're looking at this, I'm not sure why you are. I suspect a lot of the viewers of this are people who have programmed this historically and just want to reminisce a little bit, and I hope you enjoy it. I have never programmed this in my life. I am covering it because I have become a bit of a sort of an explorer in the outer realms of assembly, shall we say. So that's why I have come across this old system. Okay, so there we've used a variety of loads. Now what we're going to do this time is we're going to do some more loads, but this time we're going to load different kinds, and we're also going to do some stores. So we've got some test values here, and what we're going to do is we're going to do a series of operations on them. So we're loading the address of that set of test values into R3 here with LA, loading the address. And then what we're going to do is we're going to load R0 from the address in R3 plus an immediate offset of 0 here. And so basically going to just load that FFEEDDCC value into R0. So that's not particularly exciting. And you can see here that R0 does indeed contain that value. We're also dumping the memory before we've run any operations and also after. The reason we're doing that is we're going to store some values. Yay, we're going to do some storing as well. So the command to do a store is ST, and this is a bit of a breaking of what I said was mostly the rule before, which is the destination is usually on the left and the source is on the right of the comma. In this case it's reversed to the store command. The register is the source and the memory address is the destination. So here we're loading to the address in R3 plus an immediate offset of 6. So if we look at our memory after we've run, here is the byte 0, and if we look 6 bytes along we can see FEDC there. So that is the store that has been done by that command there. If you don't believe me, you can try loading a different value here and try running this yourself. You are supposed to take these home and run them yourself at home. You can't learn assembly just by watching me, I'm afraid. It doesn't happen. Okay, so there we stored a 32-bit value to that address there. What if we don't want to work in 32 bits? Well, we can work in 16 bits. We have a command LH, load half. So this will load a half from the address into R1. So here we are loading R1. This is going to be sign extended. So FFEE was loaded and that was sign extended, filling the top 16 bits of R1 with Fs there. We can then store that half, and we're storing that to offset 12. And you can see that has been loaded there. FFEE there has been stored to offset 12. Now, what if we don't want to store work with 16 bits? What if we just want to work in 8 bits? Well, basically, these are actually referred to as characters on this system. So a character is a single byte. So we have two commands. We have IC, which is not LC, and STC, which is store character. Now, IC stands for insert character, not load character. The reason it's referred to as insert is it changes only the bottom byte and it doesn't sign extend. The load half sign extended, this does not. So here we're loading a test value into R2, and then we're inserting a character from that address here, and we're going to load that FF part into this into R2 here. And if we look at R2, you can see R2 contains 1, 2, 3, 4, 5, 6. They were unchanged. The bottom byte has been inserted, that FF there. We're then storing that to offset 16, and you can see that all the way down there on its lonesome, there is the byte the character that we stored there. So that's how we can work with bytes. The terminology of character is a little bit odd for assembly, but if you're familiar with classic C, the character, an unsigned character, was indeed a byte. So maybe not so surprising if you think about it from a C point of view. Anyway, as I say, apart from the terminology, they're just bytes, really good old bytes. Anyway, so there we go. So we've done a variety of simple commands there with regards to loading and storing in various sizes. We're going to wrap this up, this lesson, because I suspect if you've somehow muddled across this and you've never done assembly before, your head is absolutely spinning. Z80 is where you want to start if you're just beginning. Z80 is the easiest in my opinion. But anyway, we're going to finish off with a little bit of maths, because I want to show you how to do some things with those registers you've loaded. So we're going to load some test values here. We're loading a series of hexadecimal values in here. We're showing in hexadecimal, so loading in hexadecimal makes everything nice and clear. And we're going to use some commands. Remember I said if the command ends in R, then that will be a register to register command. So AR means add register, and SR, no guesses, subtract register. So we're going to add R3 to R0 and store the result in R0. We're going to subtract R3 from R1 and store the results in R1. And we're showing the content of the registers to the screen in both cases. Okay, so let's take a peek. Okay, so here's our starting values. So we added R3 to R0. Well, you can see R3 contained the value 2, and R0 used to contain 1000, and now it contains 1002. So that addition has indeed occurred. Subtraction. Well, 1000 minus 2 in hexadecimal becomes FFE. That is correct. If you know your hexadecimal addition and subtraction, that is correct. Okay, so that's how we work with register to register. Of course, we can use memory to register. We're specifying our memory address as a label here. The assembler will work that out for us as a register offset. So our maths value 1, where is it? Let's find it. Here it is. That contains the value 3, the full word value 3 in decimal. Or it would be the same value in hexadecimal actually in that case. And so what we're doing here is we are adding that value to R0 and R1 here. So you can see here R0 contained 1002, adding 3 to that becomes 1005. R1 contained FFE, and we've subtracted 3 from that, and that becomes FFB. So there we go, that has worked correctly because we're using that math value 1. Well, we can, of course, work with negative numbers. So if we look at math value 2 contains minus 1. You can see that just there. And so we can add minus 1, and we can subtract minus 1 as well. So that's exactly what we're doing here. So when we add minus 1 to our 1005, it becomes the 1004. When we subtract minus 1 from FFB, it becomes FFC. So that's all quite straightforward. In the same way, we can also work with addresses that contain halves here. So here we are adding and subtracting the half value, math value 3. Now here we were specifying F for full word, full 32 bits. Here we're specifying H for half word, and so that is a 16-bit value. We've put 2 on the line there to keep us 32-bit aligned. That CNOP will keep us, make sure we're 32-bit aligned if everything's gone wrong, but we don't want any other problems, so we put the 2 on the same line here. We've got a value of 16 and 7 at math value 3. So let's use math value 3. So here we're adding the half value in math value 3 to R0 and R1 here. And you can see here we've added hexadecimal 10 here, so 1004 has become 1014, and FFC has become FEC because of that value 16 there, which is 10 in hexadecimal. So that's the adding and subtracting of a half here. Now, in addition to the add and subtract up here, we also have some logical commands, AL and SL. Now, these stand for add logical and subtract logical. Now, logical in the IBM370 world means unsigned, and algebraic, which would be called arithmetic on other systems, means signed numbers. Now, generally speaking, it doesn't actually matter so much whether these numbers are signed or unsigned. The important thing is how the condition codes are changed. Now, with the logical commands, the condition codes are basically set to specify a carry, an overflow, if you will. When the 32-bit value fills up and you would need an extra 32-bit value combined to make a 64-bit value, the logical ones will store that overflow as a carry, and the condition codes will be set accordingly. Now, with the algebraic ones, we don't have that. What we have is whether the value was 0, less than 0, or greater than 0, or resulted in overflow. And overflow is a very special case where the sign has unintentionally flipped. You see, if we were using this for banking, for example, and we had a customer who was heavily in debt, and they became very slightly more in debt, and that overflowed the value, and it went from a very large negative number, which that effectively is. If we reduced that by 1 and it became 7 and a large number of Fs, that's actually a very high positive number in hexadecimal representation. And so by becoming more in debt, our customer would actually become quite wealthy as an accident of our coding. And so we definitely don't want that to happen. So you know, that's why we have that overflow as a concept. Now, I'm not saying that these registers would be used in that way for banking. I'm just making the point of why the sign flipping would be extremely terrible in some cases. Now what we've done here is we've used this math value 4 here, which has the top bit set to 1, and then we're adding these logically here to R0 and R1, and you can see that that has had the effect of setting the top digit here, the top nibble, to 8 here in R0 and R1. Now these were adding logically from an address, but what we're going to do next is we're going to use ALR, which is add logical register, and so we are loading the register R3 with effectively the same value, and we're going to add logically with the register and subtract logically with the register, and then we're going to show the conditions codes to the screen. Now the important thing we're doing here is firstly we're doing them with the logical commands, and then we're doing them with the regular algebraic commands, and you will see the condition codes will be different. Now what we're going to do is we're going to do an ALR, add logical register, and then an SLR. Now the SLR is the last command we ran, and so that will be the final state of the condition codes, and we're going to run this CC test which will show the condition codes to the screen. Now what we're doing here is we are adding our very high number here from R0 and subtracting our very high number from R1. Now the first time we do this we get the condition codes 3 and 1 here, and these are the logical ones which are designed for unsigned numbers. But the second time we run this we get 2 and 3. Now this 2 and 3 have a very important meaning. Now the condition code 2 here is basically telling us that the resulting value is greater than 0. But then when we subtract that value again a second time, well, what's actually happening is we're unintentionally flipping the sign, and this is what's known as an overflow, and that's why in this case this condition code has been set to 3. Now if we were working in bank accounts and things, then flipping the sign like that would take someone who is very heavily in debt into very heavily in profit, and so that would be extremely bad. And the reason we've got these algebraic versions and these logical versions is so that we can, with the algebraic versions, have a way of detecting the overflow. It's not going to be something you're going to need to worry about though. I mean, really, I don't think there's any real case for programming this system anymore. With the Z80 and the 68000, it's a lot of fun to write little games with them and things, but with this system I think really it's purely as an educational or a reminiscence kind of thing. Anyway, I hope you've enjoyed what you've seen today. Go to my website, download the source code, the build script, try them all out yourself, and of course you can download the pre-set up server, although if you want to set up your own, just go to the Hercules website with the simulator emulator that I'm using and follow the tutorial there. That's what I did. It took me about half a day to get set up though, so I'd suggest you maybe try and help yourself out and use mine if you can. Anyway, I hope you'll stick around and see my other tutorials. We've got a whole bunch of others and we're going to cover all of the other more complex commands in those future ones. If you want to cover some other systems, please check out my other tutorials. I've got Z80, 68000, 86 ARM, every kind of system under the sun really. I also have 2 books which cover a wide variety of assembly languages, and I'm planning a third which will hopefully include the IBM370, which will be coming out next year to 2024. That will be, I don't know when you're watching this video, but the next book's planned for 2024. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching and goodbye.